Good afternoon, everyone. Now I will start my presentation. Here's the title: ModJack, hijacking the MacOS kernel. But since the title has mentioned the kernel, but our presentation would mainly not targeting the kernel itself. So, I saw this presentation and the bug is so unique, and that I will tell you in detail about how it works. So now, first of all, please allow me to introduce myself a little. My name is Zhou, and I came from China. And I currently work at for Ant Financial, the Lightyear Security Labs of Alipay. And my daily responsibilities for the product security and the offensive security research. And I've been acknowledged by these companies like Microsoft, Apple, Adobe, and VMware. So for reporting security vulnerabilities, and I'm a photoholic. And here are my blog, Twitter handle, and my GitHub profile for you to reach me out. Now, here's the outline of this topic. And first of all, we will introduce a macOS kernel attack surface. It's an attack surface, but not involving the XNU at all. And then we will analyze the bug we use to exploit to gain kernel privilege, the root cause analysis for the bug, and then is the exploit steps and the tricks we use in this. And finally, Apple did not fix the bug directly. Instead, the Apple used some mitigation to make the bug unexploitable at all. So I will take a look into these mitigations. And first of all, we have a question: why do we want kernel code execution? There's a problem on the latest version of macOS. Even a process with root privilege and not sandbox at all, it can't perform particular operations like writing to some restricted directories or just attaching the debugger to a built-in process. The KX are enforced, and besides, the KX are enforced to, if you turn on the rootless, the KX must be signed with by the certificates issued from Apple. So, which means you cannot just write your own KX and load it to the system. It will be blocked. And for those malicious softwares, it's better for them to have kernel privilege. If you have those high privilege, you can do something like hide yourself from the activity monitor, or so. So finally, the higher privilege means higher scores if you want to participate those Punijig competitions. So that's what we want for kernel code execution. The general approach for kernel code privilege escalation is to attack the kernel mode drivers or the XNU itself to control the process counter register. And then the kernel has some its internal functions to disable SIP in the kernel mode. So this is what the general approach. But what I'm going to present today is to think outside the box. Is memory corruption always necessary for this scenario? Do we have some logic bugs to attack the kernel? And do the target have always be the kernel itself or the kernel mode drivers? What about attack a user mode process? And can we just attack this user mode process to gain kernel privilege? That sounds crazy, but I will eventually prove the possibility of this way. And what about user space SIP bypass to gain kernel privilege. You see, the general approach is the other side to attack kernel to bypass SIP. What about bypass SIP to attack the kernel? That's my my approach. So I will introduce this kernel attack surface. The old days there are some examples by other researchers that they have patched the KX underlying tools to gain kernel code execution by just load then unsigned KX. First is the binary patching, the KXD processed by OS X reversal in 2013. And the second is the custom build approach by Objective-C in 2015. They both working on these binaries to patch the critical logic, like the signature check or something else, to load the evil KX. But these two previous researchers have revealed a clue that the kernel code, the signature may be checked by user space, not the kernel itself. And once you successfully load that extension without signature, it means that there's no doubt that you have kernel privileges. You can already execute arbitrary code in the kernel mode. The first one, he has patched the KXD executable, which means, but now this executable is protected by SIP. So during that time, there was obviously not rootless file system protection. And the second one, it implies that there must be some private API for these KX tools to load an extension to the kernel. And for more recent examples, IMBeer has reported this proof of concept to gain kernel privilege while just load a KX without signature. And let's look at these issues. That issue 676 is a logic error when executing an SUID binaries. When it allows the code execution as root on OS X or iOS. It looks like it's just not just a privilege escalation, but also it can give you kernel privilege. And the next issue, it is also targeting the KXD. It has some dump problems like bad path checking or ton of check, ton of use to allow it also starts from a regular user to attack the kernel. And the issue 1520, that there's a memory corruption in the KXD, is related to, let's check out these three issues. The first two are user mode only and logic, not involve XNU at all. And the third one is also user mode only, but it is a memory corruption issue, so it will be a slightly different and a little bit difficult to exploit. But these issues tell us that arbitrary code execution in this KXD process equals kernel code execution. So this is a huge attack surface. But there's a problem that there will be a question that what makes this KXD so special? Why it can control the kernel while being in just a user space process? The answer is its entitlement. What is the entitlement? The entitlement is this paragraph is copied from the Apple document. The entitlement is a bundle resource containing key value pairs that grant the executable permission to use an app, service, or technology. It's realizing plist format, which we are so familiar with, and it will be embedded in the executables code signature. So this is to protect that, to ensure that these entitlements can be modified by untrusted sources, because it's bounded with the code signature. And some of us may think, since these entitlements are important, we can gain privilege by just put these strings on our executable. So why don't we just sign in custom entitlement, like borrowing those com.apple.private. Something to add them to our binary? But if we try it, we will see that our application will be killed by task-gate D. At least some of the entitlements are preserved by Apple. If you trying to sign this in your own binary, it will be killed by task-gate D during the startup. So I have read the source code of KXD and the XNU and KX underlying tools. This graph is a little bit complicated. When KX, if you want to load an KX, you will type the command KX load, and the command line will try to communicate with com.apple.kernel extension server. This server is the KXD. Then trigger the MIG routine. This underlying KX manager, underlying load, underlying KX, to perform several checks like the file permissions, system policies, and file location. Then finally send the request to the XNU for the kernel to load that. Despite the complexity of this graph, I just want to point out a serious problem that the truth on macOS 10.13.6, the code signature of these extensions are checked by user space. The kernel just simply check. So let's just mute the other side. The only thing that kernel cares is that the caller process has the com.apple.rootless.kx secure / management these entitlements. And once so there's a command line tool, the J tool by the famous researcher, and by the famous researcher Jonathan Levin, and we will check into the KXD, its entitlement. Why is it so special? I've highlighted two of the entitlements on the text. The number one is to the com.apple.rootless.kx / secure / in management. It is this entitlement is to the privilege to ask kernel to load an extension via the KX underlying request function. And the second one is SIP related. For this executable can have write access to this specific location, a library / /stage extensions. And actually, there are 3 binaries that have this entitlement, not just the KXD, but there are the KXT load and KXT util. They also have these entitlements. So actually, all the checks that are performed by these binaries. They are implemented in this function, authenticate KXT, and it will check the file permission. It must be owned by the root and not writable by other groups. And it will check the signature. It must be signed by a valid issue from valid certificate from Apple. And during the loading process, the bundle must be staged to a protected location. So this is to ensure that when a kernel extension has been loaded and other processes have root privilege can modify this driver. And this is the another entitlement what it is for. And then it will invoke some inter-process communication with system policy D to ask user to approve for approval to load the signature. This is the user-approved kernel extension loading, or that so-called SKEL. And the most important is that if you have disabled SIP, all these checks will be skipped, except the file permission one. So what exactly is the SKEL? Apple has introduced this security measure to protect this one scenario, that if a third-party KX has the old version with known vulnerabilities, and the attacker may be able to load this extension and attack the third-party vulnerabilities. So if you're trying to load an extension, even with the signature, the Apple will show this dialog to ask user if you want to load this. And this interface is also managed by the user space and not XNU itself. And the database, there was a database in this specific location, and this database is protected by SIP as well. Even the role permission is insufficient to modify the rules. And inside the KXD, we'll have this, we'll call these functions. When you're trying to load an extension, it will check the system policy while a function named SP kernel extension policy can load kernel extension. It will internally communicate with system policy D while cross PC. And system policy D will make the decision based on these rules in the SQLite database. So if we want to bypass this security feature, the SKEL, we can do any one of the following. First is you can code execution on the rootless entitled process. Two is to inject your custom rule to the system, to the KX policy database, that SQLite 3 database. And another way is to get a task port of system policy D and to patch this specific method. You can force it to always return true, or always return yes, so all the checks will be bypassed. And the third way is to get the task port of KXD. We can patch the list function to just return just return yes, and the system policy D will never get any message from KXD. So the check will never happen. So here's the logic kernel attack service as the surface. Neither the signature nor file permission is checked by the kernel. So all we need to rule is the entitlement. And the user space process, these three are responsible to perform the signature and other validation. So if we have some user space IPC bug or anything, we can control the process counter of these three binaries. We can have the entitlement. Once you own the entitlement, you rule the kernel. So we can simplify this problem from attacking the XNU to getting the task port of this entitled process. And once you have the task port, if you have experience on programming on Mac or iOS, you have the task port, you can rule the process, you can control it to do anything you want. So here's my approach to hijack the entitlement. So here we have to do some background research for the DL hijacking on Windows. There's a known security issue, the security measure named UAC. So when we're trying to install something, something required the privilege, it will trigger the prompt. And it's kind of like SUID. When you want to do something with privilege, you can type sudo and then type the password. But on Windows, all you have to do is simply click on the yes. So there is a non-attack that you can hijack the DLL, whatever, well, import table or dynamic load library calls to inject the payload into the untrusted binary. And here is the code snippet from a leaked source from the real Trojan that it will perform the DLL hijacking to bypass to the UAC prompt to get the higher privilege. So my approach is very similar. I want to use dilib hijack to steal entitlement from these Apple sign binaries. So there are some known techniques for dilib hijacking. First is the LC underline load underline weak underline dilib. This special load command is one of the format in the metro executable. When it is a point, it has a relative at rpass, and it have this load command. It will try to locate a dilib with the specific rpass and to load an untrusted dilib outside the binary's path. And the rest of these techniques are actually the same. They are all dynamical module loading, like DL open or those NS bundle or CF. No matter what NS bundle or CF bundle it uses, the internal will always call the DL open to just load the module. And if we control the module it loads, we will share the entitlement for the host process. Now here is the bug I found with my search engine. I will introduce it at the end of this presentation. There's a framework called core symbolication. It will provide some private APIs for symbolicating and other diagnostic informations. And here is the typical crash report from macOS or iOS. If your application ever crashes, you will receive the logs from it, and you will have the context and the call stacks, and the call stacks are symbolicated in this report. You can see the symbol inside. So this symbolication is simply performed by this framework. And here's some decompiled code from the core symbolication, the function core underline external underline demangle. You'll see from the screen that it has some passes inside. There are actually 4 DL open calls. And what is the most interesting is that the last one, DL open, the argument of this DL open call is dynamically, which means it is insecure. We can trigger an interesting dilib hijack in this branch. Inside, it will, when handling those Swift binaries, it will send an external function to demangle the name. Do you know the name demangling? When you're handling the C++ programs or the Swift runtime, you will have some special chars on the function name, which is not supported. So if there is a process called demangling and mangling by the compiler to transform the symbol name to another form. So the demangling is to recover the original symbol name, and the the core symbolication framework will search this libswift.demango.dylib in the following directories. This for directory, and we can notice from the last one is a dynamically constructed path. It will be concat by a string returned by this xc select underline get developer underline dar underline path. And this internally of this function will check if there's a environment variable called developer underline dar. If it ever exists, the value will be returned. So we can simply set this environment during the process creation to control the path that of the last DL open call. But how do we reach the last branch? We can see that there are actually 4 libraries here. And how do we reach this branch? The first path is this path. It actually already exists on Hijacking. So I have a crazy idea is that since it already exists, but we have another approach to abuse the sandbox to cancel the read access. So it cannot so when it cannot read from this location, absolutely won't the DL open won't succeed. So to enforce to load our evil payload, we can apply a custom sandbox profile before spawning the entitled binary, and we can deny the file read permission for these locations, and it will finally reach the last branch. So this is the most interesting part of this exploit, that we all know that sandbox is is supposed to be security mitigation to protect the end user. But in this interesting case, it is our key point for the exploit. Now what we have to do is to find a host. Since we have the dylib hijack bug, we will need a powerful host to have the entitlement we want. So the binary must have this special entitlement that are privileged enough and have at least one code path to trigger that hijacking. So I have found this magical entitlement called com.apple.system task pods. With this entitlement, we have mentioned it before that in the latest macOS we cannot debug the internal process by Apple. But with this entitlement, we can obtain the task pod from every user mode process, even those restricted. And from this point, since we have the task pod, we will gain arbitrary entitlement, anything we want. And here's the screenshot. I wrote a little search engine for searching such targets. And then here's our entitled host, the sampling tools. They are designed for checking the performance of an application. Those information will like memory leaks, heap usage, and virtual memory mapping or string usage, etc. To obtain the information from those those built-in process, these tools must be privileged enough to be able to attach this process. So let's check the entitlement of VMweb. So you can see on the highlight the red line from this snippet. It owns this special entitlement, so it can attach to any process they want. So what about when we gain this entitlement and attach the KXD? Well, what will happen next? But here's the scenario of our exploit. The function task underline PID requires the same UID, so we cannot just run as a regular user and attach to a root process to perform privilege escalation. But if we are both root, and the difference is that my root process is not entitled and another one is entitled, we can use this this attack to bypass the SIP to inject to Apple binaries and to perform further post-exploitation. For example, here is another interesting entitlement that com.apple.rootless.install.heritable. It can access those rootless restricted files. And the most interesting is that this entitlement is inherited by this child process, which means you can just spawn a new shell. This new shell is the SIP for this new shell is totally off. Now it's time to trigger the bug. When the target process has this Swift runtime, we can simply use this command symbols the PID and to ask it to print and add this flag print demangling. If the target process has Swift runtime, if you haven't installed anything, you can just compile the Hello World Swift app. Then it will trigger the call external demangle function. And with the previous sandbox check, we can successfully fool the process to load our evil payload. And here's the code stack. I put a breakpoint on the DL open, and it successfully triggered this pass. But there is one more problem that when we try to trigger the hijack, the process crashes. So what's going on? After figuring out, I saw this from the crash log that the exception type it tells us that it crashes because of the code signature is invalid. So actually there are special flags for code signature. One of them is the library validation. If a binary is signed with this flag, it can only load those dilibs signed by the same team identifier or signed by the Apple. So the sandbox.kx has registered some callback on the mmap syscall. So when we try to violate this library validation, like to DL open and unsigned an invalid dynamical lib library, it will be killed by the kernel immediately. So the process crashes. But I have here's the word. I am old but not obsolete, said the Terminator. Let's take a look at the previous OS X release. On El Capitan, I have checked this binary. This one is from the High Sierra. It has the special flag, but when we have a look on the El Capitan, the flag is 0, which means it will not be protected from loading untrusted external libraries. And after all, the binary is signed with the entitlement and officially from the Apple. So why not just copy it to the latest macOS? And the exploit is the steps are first craft this evil libswift demangle.dilib, and then apply the custom sandbox profile to drop the access to the internal libraries. And then we can set the environment variable to control the path. And then copy this old binary from the old OS X and spawn this process to trigger the hijacking. And now there's a second stage payload that libswift demangle.dilib will be loaded into the entitled process who can call this task for PID for restricted process and obtain arbitrary entitlement. Here's our the code our SIP bypass. First, we prepare something like the sandbox profile and drop the second stage payload and set the environment. Then we can proceed spawn this Swift app to as the target for the symbols command. Now we can kickstart a SIP entitled process like this disk management did. It has the install.inheritable entitlement, which can give us a shell that will totally shut down the SIP. Now we can, the step 3 is to POSIX spawn the symbols binary copy from the L capitan. It is entitled, so now let's try to obtain symbol information to trigger the hijack. Now it triggered now the insecure DR open is triggered, and our payload will perform those process injection to steal that entitlement. Then spawn a shell without SIP or write to those restricted location. And now SIP is totally bypassed. But what we want is the kernel with privilege. So from the user space to the kernel, you must remember the graph I posted a few minutes ago. So let's change the target to kickstart this another Mac service, the KXD. We can use the same approach to gain the to get a task pod on and to get to control the KXD. So since the KXD is not library, it has no library validation, we can just use some old school dilib injection to control the process. Then we can directly ask the kernel to load our KX. The plan, we have 2 plans here. Plan A is to use the directly use this KX underline request to send a crafted packet, this MKX packet. And plan B is to we are so lazy we can when we manually craft this packet, we may handle with so many data structures, and when we are so used. But I'm so too lazy to do that. So I would rather patch some critical checks and then call its internal functions to compose the packet. So what does the packet look like? The packet starts with the MKX2 underline header, and it holds the learns and checksum version CPU type fields and the count of the bundles. The bundle is in another structure followed, and this structure can the bundle can have multiple. In one MKX packet, it can have multiple bundles in same packet, and by the end there is a plist, which is the metadata of the KX, like the bundle ID and the kernel dependencies, and some property list. But that's you can see this format is pretty complicated. So I prefer the plan B, is the lazy solution. We can simply patch those user space checks like signature validation and the staging. What is staging? Staging is the we have mentioned before that when we trying to load an extension, it must be put to some secure location, in case some other process that to modify the loaded extension. So these two checks will finally reach the CSR underline check function. It will tell the program that the states of SIP. So we simply patch this CSR check to tell the KXD that rootless is off now. And then the SKAL patch, this data bypass we have mentioned before, simply use some Objective-C method swizzling to patch this function to make it always return yes. So the SKAL is not a problem anymore. And after our patch, it is a persistent patch. When we do all this, we apply those hooks. Any user can use anyone can use the KX load commands to load arbitrary unsigned extensions in the shell. Even the SIP is on. So this is the Q switch. So now let's start a demo for the kernel privilege escalation. Now let's start a normal terminal. You can see that the UID is just a normal user, and the SIP is enabled. And we will check if there is any already loaded KX. Now let's download this payload from the remote server, and we're now checking the code signature of this KX. It's not signed at all. And this specific location, there's nothing in this location. Now we will, I will stop here. It is actually chained with another logic bug. Since all the approach we have talked in this presentation, it requires root privilege, but it can escalate from root to kernel. So the demo here, it has been chained with another bug. And now let's continue. It will spawn a new shell here, and we can check that the root list has been successfully disabled because we have loaded a new extension to the kernel. And here's the shell spawn. This shell is actually spawned by another local privilege escalation. And let's check if the SIP is really turned off. So we successfully write this file to the protected location, which means we completely disable the SIP, and this attack is can persist after can survive after the reboot. And finally, we will analyze the patch and the mitigation. The first part of this research, the SIP bypass, I actually released them as a 0-day on my blog. Why? Because during that time, I saw this on the macOS. It affects the latest macOS High Sierra at that time. But I already checked this on the Mojave developer beta. The vulnerability is gone. I think, and this is the so-called patch. The code snippets from the same function by the code symbolication that all this external dynamical loading was removed, and it only loads a hard-coded path now. I think this is not a bug fix, but it is just some code refactoring, but it kills my this brilliant bug. And before I noticed this bug on High Sierra, it was already patched in the developer preview on macOS Mojave. So, but then I've just discovered another trigger that is still present on the macOS 10.14.2 and Mojave. You can see these two terminals. First, we can start an app that written in Swift and use this command string dupes, and we can see from the and if we track the file system usage, we can see that string dupes is trying to locate the live Swift remote mirror.dylab and live Swift remote mirror legacy.dylab. Actually, it's another dylab hijacking bug that's still present on the Mojave. This bug actually locates this particular function, the underlying DL open live Swift remote mirror from directory. And it can be triggered when gathering Swift runtime information with these commands, heap, the process ID, and the string dupes process ID. It is much easier than the previous bug. And we can see from the decompiled code that it will try to locate this dynamical lib from the target process location. But this variant doesn't work anymore on macOS Mojave because because I have reported those bugs to the Apple, they have added some mitigation to kill this bug class. First of all, there's a if you care about the developer documentation, they have introduced a new feature that named hardened runtime. And the result is that even we copy those binaries from El Capitan, that the binary is not signed with library validation. If we run it on the macOS Mojave, it will act as they are signed with the flag. And only the binary is entitled with another entitlement that com.apple.security.cs.disable library validation. You only those binaries entitled with this can bypass the check. And then those sampling tools have been renamed to have their unique identifiers. And there is a new entitlement, the safe version for system task ports. You can see this, they have introduced this safe version, which means that these old binaries will not work anymore. And besides, they have hard-coded a huge list of identifiers, whitelist, in their amfi.kx policy to specify who can use this privilege to inject payload or to get a task port for those restricted processes. But there are some problems remain. KXD is now signed with the new entitlement now, which means this CS.allow unsigned executable memory. It will lower the protection of hardened runtime. So it may be still possible to. I'm sorry, the text on this is there's a typo. It is maybe still possible to attack the kernel with user space IPC bug that can control if you can root on the KXD or obtain the task port, you may have the chance to ruin the kernel again. One more thing. I have shown some screenshots of my pretty search engine. So it's written. I will introduce this and open source here. It's written in Python and based on those open source frameworks, Leaf and Radial 2, and it consists of the two parts: the data collector, the parser, and the full text search engine. It will run a disk scanner that extracts all the metadata from metro binaries and then collect the data to make it searchable. So if you want to find I will show the example then. It only supports metro formats now, and so that as well as its entitlements, code signature flags, and some. It is not a bug scanner. If you so you have already seen the QL presentation in HitBit this year. So that was a real search engine for the bug discovery, but my search engine is just some metadata search. It's not a bug scanner, but it can lead me to some valuable targets, and it's now open source. So the full text, first of all, you can just type any keyword to perform a full text search for printable strings. It's just like a simplified grep, and also suppose some other filters to make it those results more accurate, like the path of the parse, the entitlement name, or if the binary is signed by Apple or has the library validation flag, and the symbol. You can search if this or to grab all the binary to find all the binaries that have imported the system function. You can filter with this. You can locate them with these filters. And here are some examples like what do we want to search something in that the path includes WebKit or framework, or it has imported this symbol as task, or is signed by Apple, or have some special entitlement, or have some special segment. Since we have talked about entitlement, if I own Apple security, you must know the Jonathan Levin's entitlement database, the Jace entitlement database. So I have copycat my own version for it. We can here's the live demo of this. You can see it's just a web application. You can run it on your own computer, and we can like check something like a task gate. Oh, sorry. So you can, for example, to search any keywords you like like any binaries that include the keyword dash. Well, it takes so long because the results may be there are maybe so many results, and we can search for those specific entitlements. Use the filter. So all these binaries are listed here. And here's my copycat entitlement database. You can see how many different entitlements here in your system. And here are some other features like the table, the importing table for search for a symbol. Now let's hurry. There's not enough time for me, all right? So let's close this presentation for you to have time to question and answers. So what we learned from this interesting bug is that security mitigation, like the sandbox, sometimes it can betray you. And sometimes you can pound a target without even touching it. Like, I have already achieved the kernel code execution, but I did not attack the kernel itself. And here are some credits for some useful resources. Thanks for these people these resources that helped me to start my research. And also credits to this brilliant talks by other people. And finally, I named this search engine. It's just the song while I'm doing the development. I don't want to call it a mature search engine because it sounds too gay. So if you want to check the source code here, I have already published on the GitHub. And thank you for coming for my presentation. And if you have any question.
First of all, awesome presentation.
Thank you.
But is this tool, this search engine, is that also available for iOS binaries? Like, can I create a folder with iOS binaries, MacOS?
There are some. Here is a problem. I'm working on it. That's the iOS binaries. You know, the libraries are bounded in the DLD share cache. I'm working on this format. Since most of the binaries are in this cache, it is not supported now, but I'm planning to integrate it.
You can. There's an open source tool for extracting the binaries from the cache. Will probably make things easier.
I don't like that approach, actually.
No? Okay.
I'd rather do some parser to work on it.
Okay. Well, thank you.
Thank you. Any other questions? like the exploitation or the tool or the bug?
No more hands? Then I would like everybody to give a big applause for Zhou.
Thank you.